Hello everyone, I'm Xiao Tian from High Vision. Welcome to CGSP CCTV Certification Program. The topic of this course is Fundamental of Audio and Video Encoding. So from today's course, we are going to have a basic knowledge about fundamental of audio and video encoding. Okay? So after this course, I hope we can first know what is encoding and why we need encoding. And then understand different kind of encoding techniques. And at last, know different kind of encoding format and the difference between them. So this is the content of today's course. First, we will have an overview of encoding together to have a basic understanding of encoding. So let's first keep the following sets of numbers in your mind. Try to find a way to remember all the numbers here. For example, you can look for certain patterns between them. Okay? And what about this set of numbers? Again, try your best to remember all the numbers here. So it's pretty hard this time, right? So maybe some of you just remember all the sets of numbers because of your excellent memory. But it's clearly that the first 5 sets of numbers is order, right? And the second 5 sets of numbers are out of order and more difficult to remember, right? Why are the 5 sets of numbers on the left easy to remember? Because they follow a pattern, right? Remember the first set of numbers and the next 3 sets of numbers differs only by 1 last digit. And the last set differs only by 1 digit. 1, 2, 3, 4, right? We put the unordered number sets in order and remember it. That's the idea of encoding. We can compress the data according to this rule to reduce the amount of data and what we need to remember. Before we start to learn video encoding, let's first think about one question. Why do we need to encode in the security industry? So after digitalization, the amount of video data is very huge, which is not convenient to transmit and store. Through data compression, the amount of information data can be reduced. This not only saves the storage space, but also improves the transmission efficiency. Seems like now we can have an explanation of encoding now. So in broad sense, this is the process by which information is converted from one form or format to another. And in narrow sense, encoding is to transform, encode and compress data to facilitate the storage and transmission of images or sound under the requirements of certain fidelity. Encoding allows us to store, process, and transfer huge volumes of image data. So we have now a basic understanding of encoding. Then let's first focus on video encoding. So this bar chart compares the bitrate of 1080p 25Hz video transmission in different encoding formats. Bitrate is the amount of video or audio data per unit time. On the vertical axis is the bitrate in megabits per second. The horizontal axis shows the 4 encoding formats used for comparison. We can see that YUV420 format has the largest bitrate, up to 593 megabits per second. YUV is an original color encoding method, commonly used in video encoding and still images. In comparison, MJPEG, MPEG-4 and H.264 have much lower bitrate. And we can see H.264 only has the minimum bit rate of 6 megapixels per second. Does it mean that the higher the bitrate, the better? No, it's not. Of course, the higher the bitrate, the better the audio and video quality, right? Generally, the smaller the bitrate, the higher the comparison, the poorer the picture quality. But some encoding formats, such as H.264, retain some critical information while playing almost the same quality of video at a reduced bitrate. It is also important for the CCTV industry to reduce the bandwidth and retain critical information. So to sum up, we can say that encoding is a process of comparison of original YUV data into encoded data. just like the compressed file on our computers, right? When we use it for storage and transmission. They will be packed first, then when we use again, they will be unpacked. Like the picture shows, we pack the PowerPoint of this course into .ir format. The process of compressing of this original file is like encoding. And the process of unpacking of this compressed file is like decoding. So let's see what the complete process of encoding. From the very left, we can see the original YUV rate of video, for example. Then encoder finished the encoding job, convert the data, for example, into H.264. After we finish encoding the video data, we also need to encapsulate the data stream before transmission, such as PS and RTP encapsulation. The encoded and compressed audio and the video packets are encapsulated into these packets, which can be sent over the network to meet the requirements of downloading and playing. Let's take a look at decoding a little bit here. When the stream data is needed, it is encapsulated and decoded. Because the hardware display device can only support reading low YUV data. Now we knew the complete process of encoding, so let's think about questions. What exactly does the encoding do during transmission? What kind of information did it compress specifically? We know that video is made up of frame by frame. Let's see this picture in the video first. What kind of redundancy we can find in this picture? We can see that the top half of this picture is all sky, right? And we can understand that there is no key information in this half of the picture. There is usually spatial correlation between the colors of sampling points on the same surface, and the value of adjacent points are often close or the same. Like the point A and B here, right? They have almost the same information. This kind of information is called spatial redundancy. Such redundant data can be compressed using data compression techniques. Okay. So now let's look at another definition of redundancy, time redundancy. The following two pictures are two consecutive frames of a helicopter in flight. So what kind of redundant information is there in this picture? We found that the boat in the background didn't change during the flight of the helicopter, right? So at the same time, between these two frames, moving objects, the helicopter, have motion consistency, which makes the video sequence images have strong correlations, right? So these strong correlated objects or backgrounds is what we call the time redundancy. So different redundancies need to be compressed with specific encoding techniques. Intra-frame prediction is mainly aimed at spatial redundancy in the image, which is a prediction mode for the internal information of one frame image. So as shown in the figure below, when we encode an image using intraframe, we first segment the image into these white areas. These blocks we call them macro blocks. The area on the left is the area that has been encoded, and the white area on the right is the area to be encoded. Let's say we are going to compress the area within the red block. The encoder can find the same macro blocks in the same frame. After it finds the same macro blocks, we can let the encoder to copy this macro block without having to search for another frames. For example here, according to the internal continuity and correlation of this frame or image, T1 to T6 can be predicted directly by the encoded color blocks. Interframe prediction is mainly used to eliminate time redundancy in video sequence. First of all, the current frame in the video sequence is basically the same as the background of previous frame. So the background of the previous frame can be directly used to replace the background of the current frame after processing. There is no need to encode the current background. Like in the pictures below, these two pictures are two consecutive frames. We can see that although the car is moving fast, its background remains the same. Now we want to compress data of this card in the dotted red line box. According to intra-frame prediction, unlucky we can't find the same part, right? But we find the card in the frame 2, right? This moving card is basically a displacement between these two frames. The difference between two cards' microblocks in these two frames seems very small, right? So our encoder can compress the data by the displacement of this card's microblocks. We can add a vector to this card moving the previous frame of the image and make it do a displacement based on the background to get the current image. This is what we call interframe prediction. Okay, so now we know what is encoding and we also know some encoding techniques. Let's go back to the memory game we did at very first beginning. I believe you still remember how we remember these 5 number sets, right? Remember first number set and then remember the difference between those number sets, right? So if we take 5 number sets as 5 frames, which contains different content, so in the video encoding, we call the first number set as I frame. We also call it intro picture, which contains some key information. And we call 1, 2, 3, 4. We call it as P frame. So we also call it predictive frame. It represents a difference from the previous frame. After learning about redundancy, interframe, and intraframe prediction, let's look at 2 basic frame types, I-frame and P-frame. An I-frame is also called a key frame, like I said, and consists only of microblocks predicted within one frame. Each microblock in one I-frame can only match other microblocks within the same frame. Okay? So which means that it can only be compressed using spatial redundancy within the frame. P-frame stands for predictive frame. In addition to spatial prediction, it can also be compressed by time prediction. The P-frame is used for motion estimation by referring to the previous frame. Frame I and P are shown in the figure above. As discussed earlier, P-frame refers to previous I-frame or P-frames, alright? Now, let's think about one question. What will happen if a frame loses? In a complete sequence, if any frame is lost, all subsequent frames cannot be recorded. Wait until you hit the next I-frame. In practical, frame loss may lead to stutter, black screen, splinter screen, and other problems. And that makes perfect sense too. If my keyframe goes to 0 or is lost, so I don't know what the difference is from with the previous frame, right? So it doesn't change between frames. So